found out the common contact area, it would be that area right there. So it's going to be how far it bears by the width of the thing sitting on it. That's this. The force is a reaction. What does it have to hold up? So that's how you figure it out. So hopefully, we got people going to table on page 676 and pulling out a number. It's the area of the beam, the cross-sectional area of the beam. Cross-sectional area of the beam is here. If I looked at it, it's this. It has nothing to do with it. The width does, but the height has nothing to do with the common area. So take a look at one thing sitting on the other, wherever they're touching, wherever they're sitting on each other, that's the bearing area or the contact area. So you guys are doing a problem. I'm going to do 5.6a. Okay, so let's take a look at that. And 5.6a. My book's just about had it. 5.6a. That is on page 210. It says, I have a 6 by 12 beam of Doug fir larch number 1. Doug fir larch number 1 has 3 inches of end bearing to develop a reaction of 5,000 pounds. So here's what I've got. Got a beam sitting on it's got 3 inches of bearing. It is a 6 by 12. 12 inches tall, 6 inches wide. The common area is the width of the beam times 3 inches. What is a 6 by 12? If you go to the back of the book, 676, and you grab a 6 by 12, you got yourself a member that is 5.5 inches wide. So it's going to be 5.5 by 3. So if I put it in here, FC perpendicular, 5,000 pounds, 5.5 by 3. There's how much force or stress is pushing down with. So 5,000, so 5.5 times 3, invert times 5,000, 303.03. Is it going to work? Well, it's a 6 by 12, so it's bigger than 5. So I go to the table. I get to the table. It's a beam, so it's cell 2. It's number 1 Doug fir larch, so I'm there. And I got to go over to the FC perpendicular, and when I hit that slot, it says it's 625. So, is that bigger than that? Yes, it is, so it's okay. That's it for bearing. Okay? Remember, common area, contact. Reaction, okay? Whatever force needs to hold that up, that's the force that's sitting on the wall or the beam or the girder with. That's what causes the bearing stress. Okay, we are on the brink of being done. Number 7, 5.7. Don't use the book. Put an X through it. We're not going to use it. Okay? So for 5.7, the only thing you got to worry about is page 114. If you start using the book, you're going to get yourself in a pickle. You're going to get, mentally, you're going to get tossed where you don't want to be. So let's take a look at what we're going to do. If you go to page 114, okay, you got a bunch of scenarios. So needless to say, the scenario on the test is going to match the pictures on page 114. If you look at it, what is deflection? In that table, it's this, delta, change. Okay, that's what that stands for. So our equation is going to look like this. Let me put your general equation. Big delta is greater than or equal to little delta okay. Every equation that you look at has an E and an I in it. Okay, so the numbers, you can figure out the P's and the W's, that's no problem, and the L's, that shouldn't be a problem for you by now, but the E and the I may be. Okay, E comes from table 5.1. Okay, so if you need E, go to table 5.1. The other one is the I. Go to the table on page 676 and 677 and go to the IXX and grab it and you're done. Okay? What is the big delta? The big delta is code driven. This is code. And it's going to be L over a number. And I'll give you the common numbers you'll see in the code. You can go to a lot of building supply houses and you can get things like thin set for tile. You can get materials associated with drywall, and they all have these numbers on them, L overs. They're all over the place. Guys in the field have no clue what they're looking at, but it's a lawyer thing. The lawyers put that in there. The guys in the field don't know what they're doing. They get in a lawsuit. The lawyer will say, well, didn't you read the spec? You didn't follow the spec. That's why it failed. That's why we're here. Okay? So this is going to be L over. L is the span in inches. 240, 180, 360 is a constant. The bigger the number, the more stringent the spec. If I have a beam that happens to be, let's make it 30 foot long. If I have a criteria that says the maximum deflection is L over 180, big delta is going to be 12 times 30 over 180. 2 inches. Okay? If I've got L over 360, maximum deflection is 1 inch. If I have L over 480, three-quarters of an inch. So you can see as the L number gets bigger, the allowable deflection keeps getting smaller. I had a guy one time give me a house plan to look at, and it had designed the floor for L over 640. Okay? If you go to code, you go to the code, code says residential floors need to be designed for L over 360. That's what it says, written right in it. They wanted me to go L over 640. My question to that designer was, is this for a herd of elephants? You know how much money it costs to change a floor system from L over 360 to L over 640? Lots and lots of money. The members got to get a lot bigger. Materials got to get a lot stiffer. It costs a fortune to do that. Worthless. It was happened to be a young guy that was just getting into it. And I asked him, where the hell did you get this? Well, I didn't know what to use, and it seemed like if I went bigger, it would make I'd be less prone to be sued. So I thought a little bit of money that you had to spend would save me from getting sued. I might as well do it. Pretty good logic, huh? It doesn't work quite that way. So let's do a couple problems. It's not too hard. Let me put, this is going to be delta. So I'm going to do B first, D second, and E third. These go real quick, not much to them. Okay, let's look at 5.7. 5.7, where are you at? If I can hold this book from falling apart.